All right, let's take a look at this review problem. Y double prime plus 2y prime plus y is equal to t plus 2 times e to the negative t. And I'm going to do this one two different ways. One's with the method of undetermined coefficients, and then after that's done, I'll do it by a variation of parameters just for the sake of review. First step for either technique is to find the characteristic equation. Characteristic equation is going to be r squared plus 2r plus 1 is equal to 0. And of course that factors as r plus 1 squared is equal to 0. So r equals negative 1 is a double root of the characteristic equation. And therefore the homogeneous part of the solution is going to look like this. Y is equal to c1 e to the negative t plus c2 t times e to the negative t. So that's going to be the form of the characteristic part of the solution. That's part 1 of the solution. Part 2 of the solution is to find the particular solution. First, let's try the method of undetermined coefficients. So y of t equals, here I have a linear term t, and so I have at plus b to be the linear term that matches. 0 is not a root of the characteristic equation, and so I can just simply write at plus b as my proportion. Remember, don't forget the plus b. Even this is linear, even though there's no constant term, I still include the constant term down here. Plus, okay, here I have polynomial times e to the minus t. Polynomial degree 0 times e to the minus t. So ordinarily I would have polynomial degree 0 times e to the minus t. The catch, of course, is that negative 1 is a root of the characteristic equation. In fact, it's a double root. So because it's a double root, I have to include an extra t squared there as my guess for the particular solution. So that is the form of the solution that I will guess. So let's now figure out the first and second derivatives. Y prime is equal to a plus, okay, take the derivative of this, I get 2ct, derivative of the first, times the second. Then I have the first times the derivative of the second. And the effect is that I have a minus kick out. Then I take the second derivative. Here the second derivative of the constant is 0. Here, if I take the derivative, well, actually, let me just go to the top here. The second derivative of the first is going to be 2ct e to the minus times the second, plus 2 times the first derivative of the first times the first derivative of the second, and then the first times the second derivative of the second. And I shouldn't have had a t here, I apologize. So second derivative of the first is going to be 2 times c e to the minus t. Okay, so let's form this left-hand side, y double prime plus 2y prime plus y. So I get 2c e to the minus t minus 4ct e to the minus t plus ct squared e to the minus t. Then I add 2 times the derivative, plus 2a, plus 2 times the derivative. We get 4ct e to the minus t, minus 2ct squared e to the minus t, and then add on the original function. So at plus b plus ct squared e to the minus t. And so we've rigged things so that this cancels and also these three cancel. And so this left-hand side is equal to at plus b plus 2a plus 2c e to the minus t. And that's supposed to be equal to the right-hand side, which I'll copy down at the bottom, t plus 2e to the minus t. Okay, so now I just have to match parts. So that matching up, I get a is equal to 1, because this matches this. Also, b plus 2a is going to be equal to 0, because this constant matches the 0 over here. And so that implies that b is equal to minus 2. Lastly, this part matches this part, and so that means that 2c is equal to 2, so that c is equal to 1. Okay, so that gives me my particular solution, that y of t is equal to Well, the form is up here, so a is equal to 1 plus b was equal to minus 2, plus ct squared e to the minus t, c is equal to 1. So plus t squared e to the minus t. And so that means the general form of the solution is going to be equal to c1 e to the minus t plus c2t e to the minus t plus t minus 2 plus t squared e to the minus t. And so that is the general solution of this second order non-homogeneous linear equation. Okay, so for the purposes of a test, that's certainly going to be sufficient for providing the answer. However, there is an alternate way of doing this, which I would like to demonstrate for the purposes of review using the Wronskian. So here we go. So starting over, we found that y1 of t was equal to e to the minus t, and y2 of t is equal to t times e to the minus t. So before using variation of parameters, let's find the Wronskian. So the two solutions are up here, e to the minus t, t e to the minus t. Let's take the derivative, negative e to the minus t. Derivative of this by the product rule will be derivative of the first times the second, plus the first times the derivative of the second. Okay, so we take the determinant, we get e to the minus t times e to the minus t minus t e to the minus t. Then I have minus multiply this way, t e to the minus t times e to the minus t. And then what's going to be left is e to the minus 2t, because when I multiply out, that's going to cancel out this part. Okay, so to apply the variation of parameters, we have to figure out a couple of integrals. u1 of t is equal to negative integral of y2 of t, g of t, divided by the Wronskian of t, dt. So negative integral y2 is equal to this, t e to the minus t. G of t was the right-hand side, and the original right-hand side is up here, t plus 2 e to the minus t, divided by the Wronskian, e to the minus 2t dt. Okay, so multiplying out, we get negative integral. Let's see, so we get t squared e to the t dt, and then we also have a second integral, which is a little bit easier, 2t dt. So first part, I have t times t for t squared, then e to the minus 2t in the bottom, comes up as e to the plus 2t, multiplies this, I get this. And if I multiply these two together, e to the minus t, e to the minus t becomes e to the minus 2t, which cancels the bottom, and I get this. Okay, now clearly this integral is easy to get, negative t squared. This one I have to do integration by parts and do parts twice. So u is equal to t squared, dv is equal to e to the t dt. So that means that v is equal to e to the t, and du is equal to 2t dt. So starting the integration by parts, we get minus u times v, t squared e to the t. Then minus and minus becomes plus integral of v du, 2t e to the t dt. Okay, we do the integration by parts again. U is equal to 2t, dv is equal to e to the t dt. V is equal to e to the t, and du is equal to 2 dt. So minus t squared e to the t, plus u times v is 2t e to the t, minus integral of v du, so 2 e to the t dt. And so finally, after all that, we get minus t squared e to the t, plus 2t e to the t minus 2 e to the t, plus a constant. And so that is the first integral that we need in order to do variation of parameters. The second integral we need is integral of y1 of t, g of t, divided by w of t dt. So its integral y1 was e to the minus t. G of t, again, was the right-hand side of the differential equation, divided by e to the minus 2t dt. Okay, multiplying out. Let's do the right side one first. E to the minus t becomes e to the minus 2t, canceling out the bottom, so I get integral of 2 dt. The second one, I get t times e to the minus t over e to the minus 2t becomes t e to the t dt. All right, first integral is easy to get. The second integral, I'm going to have to do integration by parts, and I'll pretty much do the same thing here except without the 2. So u is equal to t, dv is equal to e to the t dt, v is equal to e to the t, and du is equal to dt. So u times v, t e to the t minus integral of v du. So I get 2t plus t e to the t minus e to the t plus my constant c2. So here's my u1 of t, my u2 of t I just computed, and I will now use both of those integrals in order to figure out the form of the general solution. So the form of my general solution is going to be y of t equals u1 of t times y1 of t plus u2 of t, y2 of t. So u1 was equal to this up here. So I have negative t squared minus t squared e to the t plus 2t e to the t minus 2 e to the t plus c1 times y1, which was e to the minus t, plus u2, which we just got, 2t plus t e to the t minus e to the t plus c2 times t e to the minus t. And so we have a fairly large, hideous mess to simplify. Equals. Okay, first the constant c1 e to the minus t plus c2 t e to the minus t. So that's out separate. Okay, so let's start multiplying. We get minus t squared e to the minus t. That's this part. Multiplying these two together, I get minus t squared. Multiplying these two together, I get plus 2t. Multiplying these two together, I get minus 2. Okay, then doing the rest, here we get plus t squared e to the minus t from these two terms. From these two terms, I get plus t squared. Then on these, I get minus t, and I've already dealt with the constant, and that's up here up front. All right, so t squared cancels negative t squared. What else can we do? We have that 2t, let's start over, c1 e to the minus t plus c2 t e to the minus t. 2t minus t is plus t. There's my minus 2. Over here I have 2t squared e to the minus t minus t squared e to the minus t gives me plus t squared e to the minus t. So that took care of those two. I've done those two. I've done that. And I believe those are all the terms. And that should match the solution that I had earlier. So once again, variation of parameter works. However, it just usually produces a lot more work than using the technique of method of undetermined coefficients.